Hey, physics, welcome to another flipped lecture. We're diving into chapter 10 today. It's kind of a potpourri chapter. There's several ideas here, but they're all tied to the concept of the conservation of energy. And so we're looking at conservative forces and non-conservative forces, and we're applying that to a couple of different ideas, including free fall and simple machines. All right, so here we go. Conservative forces and mechanical advantage. We're looking first at the idea of conservative and non-conservative forces. So we dealt with this at the end of chapter 9. They introduced the concept to you there. We're going to be applying it a little bit more specifically in this chapter. So just some clarifying vocabulary. All conservative forces are central forces, meaning when you're looking at conservative forces, we consider all the objects as point masses. So if we're talking about me in free fall, jumping out of an airplane, which I would never do, but let's just say we were talking about that, then you don't really care about the shape of my body and how much my hand weighs versus my foot. You're just going to say there's this thing falling out of a plane and it weighs, 100 kilograms or something like that. And that would be good enough to describe me. You consider me as a point mass. And then you could also look at the Earth as a point mass and take all of its very large mass and shrink it down to a point representing the center of the Earth and all of its mass, and talk about how far away I am from the center of the Earth, and considering us both as point masses. That's what central forces do. So we don't care about how the mass is distributed throughout the object. We're going to look at everything as a point mass when we talk about central or conservative energy. And basically, most of physics consider things as point masses until you get into air resistance, which we won't deal with very much. Okay, but we deal with it a little bit just in this concept here with terminal velocity. I won't ever make you calculate this, but you should be familiar with the term. Okay, so if something is falling out of an airplane, like not me, but somebody less intelligent, they're jumping out of an airplane and they're falling, there comes a point at which the air resistance on them is counteracting the acceleration of gravity. So you've got this object falling and gravity is pushing it down, friction, wind resistance is pushing it up, and when the down and the up balance each other, then you have achieved terminal velocity. And at that point, it's no longer a conservative system because the object is still losing potential energy, right? It's not as high as it used to be, and it's going to get lower. So it's losing potential energy because of gravity, but it's not gaining any more kinetic energy because it's not speeding up. So where is the loss of energy going? There is potential energy, and it's going down, and energy is conserved, but it's not perfectly conserved into kinetic energy at all times. So the mechanical energy is changing. Where is it going? Well, in free fall, you reach this point of terminal velocity, and then the energy that you're losing because of the loss of your potential energy is going into other forms of energy, usually heat. The wind pushing up on you, which is canceling the force of gravity pulling down on the object, is going to, it's friction, and it's going to give off heat. So objects in free fall tend to heat up. Now, skydivers don't experience this very much because the evaporative cooling effect of all of the wind blowing past them, it still feels cold to be in free fall. But their clothing and things of that nature are going to be slightly warmer when they get to the ground or when the chute opens than when they left the plane. But free falling for just a small amount of time at not that fast of a speed, you're not going to notice that if you're the skydiver. If you drop a rock out of an airplane and pick it up as soon as it lands, it may be warm to the touch, but it's not going to be, oh, wow, that's really hot. Where you really see this is in the space shuttle or any kind of re-entry vehicle from space. This is an artist's conception of the space shuttle re-entering, and all of this heat energy is being given off by the space shuttle as it's decreasing from Mach 18 to Mach 0.5, which is the speed at which it lands. So it is cutting a lot of velocity out. It's losing a lot of potential energy, and the atmosphere is doing that slowing down, right, in free fall. And all of this heat is given off as the space shuttle re-enters. This is Space Shuttle Atlantis, and when it was mothballed and put in the museum here, they didn't clean it up. So this is how Space Shuttle Atlantis looked when it got down from its last mission. And you can see all of the discoloration on the heat shields and how orange it is. And that's because all of these tiles got burned and discolored by the heat of reentry. So large objects that come in at very high speeds achieve terminal velocity, and all of that energy is shed in the form of heat, and you can see that here. Okay, so terminal velocity is kind of related to the idea of escape speed. So terminal velocity has to do with the strength of the force of gravity on an object versus friction. Now we're going to look at how fast do you have to go to escape the grip of gravity. Okay, so conservative energy, conservative forces, again, we're thinking about the fact that kinetic energy, total kinetic energy, and total potential energy are related, right? The change in kinetic energy equals the change in potential energy. Remember the example we did in class with the skateboarder who's going at a certain speed along the ground, and then he goes up the ramp, and eventually his velocity is zero because all of his energy is turned into potential energy, and then he hangs there for just a split second before he comes down, and now his potential energy is becoming kinetic energy again. That same idea is tied to the concept of escape velocity. If you're the little boy doing your skateboarding and you hit the ramp, the faster you're going, the further away from the Earth you're going to be able to get before Earth's gravity slows you down to zero and starts returning you to the surface of the Earth. If you're going fast enough, then you can achieve an infinite distance before gravity grabs you. In other words, gravity won't grab you because you are going away from the Earth fast enough that the acceleration of gravity can't slow you down to zero before it has a negligible effect on you. Okay, that's escape velocity. The little boy would have to be going very fast to hit the ramp and achieve escape velocity and find himself in orbit. But rocket ships do this all the time, right? So what we need to do is calculate the escape velocity. Now, some interesting things about escape velocity is that the escape velocity does not depend on the object leaving gravity. And at first you don't understand why that is, but your book takes you through the steps in deriving the equation that I'm just going to show you. And in the derivation that it takes you through, you can see how the mass of the object leaving gravity doesn't matter. It gets canceled out in the course of the derivation. So the little boy on the skateboard, if he could go fast enough, would achieve escape velocity on the ramp. And a rocket ship has to achieve the exact same escape velocity, even though the rocket ship weighs a lot more than the little boy. Okay, so the mass of the object leaving the larger object's gravity is irrelevant. All that matters is the mass of the object that you're leaving and the radius at which you're going to measure escape velocity. So for us, the measurement is the surface of the Earth. How fast do you have to be going when you leave the surface of the Earth to achieve escape velocity? And then we need the gravity constant and the mass of the Earth. So here we are. The escape velocity is the square root of twice the gravity constant, big G, 6.67 times 10 to the, I think it's negative 11. And then the mass of the Earth, and then the radius that you are measuring the escape velocity. Okay, so this is going to be the radius of the Earth, and this is going to be the mass of the Earth. And it's true for all objects. Now, there's also escape velocity for the solar system. If we're going to not just leave the Earth, but we're going to launch a probe and we want it to leave the solar system like Voyager 1 and 2 have done, then we need to have not just the mass of the Earth, but we're looking at the mass of the Sun. Now that's going to be a lot larger mass, and the escape velocity is going to have to be a whole stinking lot faster. Oops. But we can do the exact same equation. So the escape velocity will be the same for every object leaving the gravity influence of some other object. So every object leaving Earth, same escape velocity. Every object leaving the solar system, same escape velocity, etc. Okay, so let's do an example problem with that. Here we have Space Shuttle Columbia lifting off for its last and tragic flight. This is the liftoff that ended in disaster for Columbia. But we want to look at how fast it is leaving the Earth, right? So Earth's radius we need 6,371 kilometers. Now that's not meters. Our equation requires meters. So that's actually 6,371,000 meters. I'm going to turn that into scientific notation just for ease of use and say 6.31371 times 10 to the 6th meters. By the way, if you see this E in the middle of a number, that's the same as times 10 to the whatever power. Okay, it's just a quicker way of writing that. So 6.371 times 10 to the 6th meters. That's the radius of the Earth. Earth's mass, 5.972 times 10 to the 24th kilograms. That's a lot of kilograms. And then the value for G is 6.674. Huh, look at that. E, not D. Editing on the fly. Times 10 to the 11th, 10 to the negative 11th newtons meters squared per kilogram squared, and all of that nasty unit just cancels out in this equation. So it leaves us with meters per second at the end, so don't get stressed out about that unit. Okay? Oh look, I see the D again. That's fun, because it's not D, it's E. That's what happens when you copy things. All right. Escape velocity is the square root of twice the gravity constant times the mass of the Earth divided by the radius of the Earth. So let's plug those numbers in. I'm going to leave G by itself just as a G for a minute so the numbers don't get overwhelming. Okay, so 2G times the mass of the Earth divided by the radius of the Earth. So I'm going to leave G like itself, multiply 2 times this, and I get this beautiful number. 2 times this and divided by this. There you go. I get this beautiful number, and these ugly units, don't worry about those units. They're all going to go away in just a moment. Now I can take G and multiply it by this big nasty number. So G times this didn't all fit on one line. And I get this beautiful number. Okay, and again, ugly unit, but you know what? That actually reduces, once you take the square root, reduces down to meters per second. So we're just going to leave that by itself. 1.251 yada yada times 10 to the 8th. Okay, take the square root of that, and I wind up with this number in meters per second. Way too many digits. Here I look back, I had 4 and 4 and 4 significant digits, so I'm going to leave myself 4 significant digits in the answer. So that's 1.119 times 10 to the 4th meters per second. That's really fast. That's about 11 kilometers per second. 11 kilometers per second. Okay, that is way fast. Way fast. And that is how fast Space Shuttle Columbia needs to be going here to escape the influence of Earth's gravity. Crazy fast. So that's escape velocity. Replay that example if you need to. Conservative forces and mechanical advantage. Now we're slipping into machines, to the mechanical advantage part of this, right? Machines do not create energy. Machines, simple machines, we're not talking about motors and engines here, right? This is like levers and pulleys. Simple machines do not create energy. They spread out the work. Remember that work is force times distance. Well, if you want to do the same amount of work, but you don't want to apply as much force, you need to do that less force for a bigger time, for a larger distance, in order to get the same amount of work done. That's what machines do. They spread out the work so that you can put less force in and get the same work out. You just have to do that less force for a further distance. Okay? There's 2 major categories of simple machines. One is an inclined plane and one is a lever. Everything else fits into that bucket, one of those 2 buckets. Okay, we covered the 3 kinds of levers in physical science, and they are covered again in your chapter. I'm not going to go through them here. That's a review. If you don't remember the 3 kinds of levers, look at them in your book. Okay, there are pulleys are also a lever, which at first you go, what? But when you look at the way that it works with the size of the wheel and the axle being the fulcrum, then it actually is a lever, and it's just a weird kind of rolly lever. So we'll be using the same equations for those. And wedges and screws are inclined planes. So a knife, a scalpel, an axe, a ramp, a screw, it all is the same idea. And we'll go through some examples of those later on here. Ideal mechanical advantage. Why do you use a machine? You use a machine because it allows you to do the same amount of work with less force. How do you calculate the benefit that the machine is giving you? you use something called a mechanical advantage. There are two kinds of mechanical advantage. One is the simple mechanical advantage that ignores friction, where you just look at the tool and say the tool should be able to multiply my force to this degree, and then you're happy with that and you move on about your life. That's called ideal mechanical advantage. The other mechanical advantage that we'll get to in the next slide is actual mechanical advantage, when you allow friction into your equations and you say how much did it actually multiply my force, not how much should it multiply my force. Okay, so ideal mechanical advantage first ignores friction. Ideal mechanical advantage, or IMA, is the force that you get out of a machine divided by the force that you put in the machine. So you're looking at how much your force was multiplied here. You could also look at it as the distance that you had to do the work versus the distance that the machine did the work. And so either way, you're going to get the same answer, distance in divided by distance out, or force out divided by force in. Either of these equations will get you the same number. Okay. And you could, I suppose, set these two as equal to each other and solve if you knew some of those terms, but not the other. So for an ideal mechanical advantage of greater than 1, you put in less force for a longer distance to get work done. So this is like using a ramp. Okay, if I need to lift a heavy object 1 meter, I would rather push it up a 7-meter ramp and put very little effort into it for 7 meters to get the thing 1 meter off the ground, rather than just deadlift the thing straight up 1 meter. Okay, less effort, longer distance, I get the same amount of work done, and that would be an ideal mechanical advantage that's greater than 1. For an ideal mechanical advantage less than 1, I'm going to put a whole bunch of force in for just a short distance, and I'm going to get less force but at a greater distance. An example of this is the muscles in your arm. So God designed our bodies so that I can't get the image right. There you go. So I just pull a little bit of distance here on my arm. My muscles are only contracting just a few centimeters, but that few centimeters, using my arm as an ideal machine, moves my fingers a long distance, even though my muscles are only contracting just a few centimeters. So in that example, the mechanical advantage of my arm is less than 1. It's going to be a fraction. And my muscles actually pull a lot harder on the arm than the force at the end of my fingertips. But the trade-off for that is that I get a lot more motion out of my arm, and I don't have to have really long muscles to get my arm to move. Okay, so those are some examples of an ideal mechanical advantage greater than 1 or an ideal mechanical advantage of less than 1, and why you would want either of those circumstances. Okay, the actual mechanical advantage accounts for friction, and we always measure this as opposed to calculating it. You can't really calculate AMA. You can measure AMA. You look at the force going into the system and the force coming out of the system. You calculate the work done, and then you can see how much you actually were helped by the machine, and not what theoretically the machine should have done. This is always measured rather than calculated. Okay. All right. Okay, calculating your IMA with various simple machines. The IMA, when you look at an inclined plane, is the slope length divided by the rise. So how long is your ramp, and how high did it lift the object? Or if you're talking about a knife edge, it's the length of the ground slope of the knife blade and the thickness of the blade. Or for a screw, you can use the same kind of thing, okay? Slope length versus rise. That'll give you the inclined plane ideal mechanical advantage. For a lever, it's the length of the effort arm divided by the length of the resistance arm, and that will calculate the ideal mechanical advantage there. For pulley, it's just the number of cables holding the weight. Okay, so let's look at examples of all three of these. And so here's a pair of, I don't know, sound equipment people, and they're bringing some equipment up to a stage, and rather than pick this box up 0.86 meters straight up off the ground, they're going to use their 3-meter ramp to bring it up to the top of the stage. So what's the ideal mechanical advantage here? The ideal mechanical advantage is the slope length divided by the rise for a ramp. So the slope length here, it's a 3-meter ramp, and they got it 0.86 meters off the ground by using that ramp. So 3 divided by 0.86 is an ideal mechanical advantage of 3.5. Now there are no units here. Notice this is meters divided by meters. So the units cancel out. Ideal mechanical advantage and actual mechanical advantage do not have units. Okay, so you won't see any units after these numbers. So that's a pretty simple idea. Let's look at a lever. Here we've got a worker trying to lift a rock. And how much force does the worker need to apply to the effort arm of this pry bar if he is to overcome the weight of the rock on the other end? From the fulcrum, he's got a 1.2 meter effort arm. He's got a 0.24 meter resistance arm, and the rock itself has a mass of 82 kilograms. So let's calculate the ideal mechanical advantage first. It's effort arm divided by resistance arm. So here 1.2 meters divided by 0.24 meters is 5. And again, no unit. It's just a multiplication factor of 5. Okay? And the ideal mechanical advantage is the force out divided by the force in. And so I'm going to rearrange because I know the force out and I know the ideal mechanical advantage. What I don't know is the force in. So I'm going to rearrange this equation to solve for Fn. Okay? So if I multiply both sides and then divide, I can rearrange the equation to be force in equals force out divided by mechanical advantage. So I'm going to say, what is my force in? It's the force of the rock because of gravity, right? The weight of the rock. So its mass is 82 kilograms, accelerated by the force of gravity, and then that's going to be divided by 5, my ideal mechanical advantage. If I do this multiplication out, I have 804.42 newtons divided by 5. I divide that number by 5, I have 160.884 newtons. Correct for significant digits here, I have 2, I have 2, I have 2. So 160 newtons. The guy's got to push down with 160 newtons to get this rock to move. Okay, that's what the lever does for you. Here we have how much force does this young boy need to employ to lift his mom, who weighs 62 kilograms off the deck of their boat. And so I'm sure she's just teaching her son physics. I don't know why else she would make him lift her off the deck of the boat, but I'm sure this is a homeschool physics lesson here. Here we have a block and tackle pulley system with 1, 2, 3, 4 laps of the cable. You don't count this one. This is considered like the effort arm, right? This is the resistance. So 1, 2, 3, 4 laps of the rope, and so the mechanical advantage should be 4. So the mechanical advantage is 4. Mechanical advantage is force out divided by force in. Again, rearranging to solve for force in. Force in is force out divided by the ideal mechanical advantage. His mom weighs 62 kilograms. That's the acceleration of the force of gravity. So her force with which she's being pulled to the earth is 608.22 newtons. Divide that by my mechanical advantage. I have 152.055 newtons. I've only got 2 significant digits, 150 newtons. This boy's got to pull with 150 newtons to get his mom off the deck of the boat. Okay? If you need to see any of those again, pause the video, go back, and look at them as many times as you need, or you can post some questions below, and we will deal with them tomorrow in class. One last concept, and that is the idea of efficiency. Efficiency is the degree to which the mechanical system is conservative. So we're going back to the concept of conservative energy here. Mechanical advantage, in an ideal sense, ignores friction. In an actual sense, we have to know that friction exists. The ratio between the two is efficiency, and we use the Greek letter eta to represent that. That is not a lowercase n. Okay, a lowercase n would have both legs of the letter the same length. The second leg of this letter is longer. That's the Greek letter eta. Okay, so we use eta to represent efficiency, and we just divide the actual mechanical advantage by the ideal mechanical advantage and multiply by 100%. It's just a ratio. Okay, the higher the eta, the higher the efficiency, the more AMA approximates IMA, and the less energy is lost. So last example. We have the same situation, the boy pulling his mom off the deck. We know that the ideal mechanical advantage is 4 because we can count the laps of the rope. But there is friction in this pulley, and the rope does stretch a little bit, and so some of his energy is lost. We want to know what's the actual mechanical advantage, and then what is the efficiency of this pulley system. Okay, so if we measure the force that the boy is pulling with, and he actually pulls with 161 newtons to get his mom off the boat, and it should have taken 150 newtons according to just our simple math. Then what's the efficiency here, right? So actual mechanical advantage is the actual force out divided by the actual force in. So there's his mom's mass, there's the acceleration of gravity, that part didn't change, but he didn't pull with 150 newtons, he pulled with 161, right? And so here's the actual force of her weight on the earth, and here's the actual force the boy put into the pulley. The actual mechanical advantage is 3.777639, and so the ideal is 4, so we need to compare these two. Eta equals the actual mechanical advantage divided by the ideal times 100%. Here's the actual mechanical advantage divided by the ideal times 100%. We get this long number. Multiply that by 100%. We have 94.444093%. Again, I only have 2 significant and 3 significant. I got to go with 2 significant digits, so 94% efficiency, which means that 6% of the energy that he put into the system is lost to the friction of the wheels, the rope stretching a little bit, maybe the pulley squeaked and we lost some energy to sound, but whatever happened, he got 94% of his force actually into the system to move his mom. Alrighty, any questions, post them in the comments field below. I'll see you tomorrow. God bless you. Have a wonderful night.